Good afternoon, everyone. Welcome to the 2022 J. Tuzo Wilson Lecture. My name is Qingya Liu. I'm the current J. Tuzo Wilson Professor of Geophysics in the Department of Physics and Department of Earth Sciences at University of Toronto. The annual Tuzo Wilson Lecture was established in 1995 to commemorate the life and work of Professor J. Tuzo Wilson. Professor Wilson was one of the most imaginative Earth scientist of his time and one of the founders of geophysics in Canada. He made decisive contributions to the revolution in earth sciences in the 1960s and 1970s, brought about by the establishment of plate tectonic paradigm. His major contributions include contribution to the idea of ocean floor spreading and hotspots, recognition of transform fault as a type of plate boundary, and the life history of oceans known now as the Wilson cycle. Professor Wilson became the only professor of geophysics in Canada in 1946 at the Department of Physics, and he served as chair and then later vice president of the International Union of Geodesy and Geophysics, known as IUGG, in years leading up to the International Geophysical Year, IGY, known as IGY, of 1957 to 1958. In his later career, he served as principal of Arundel College, which is later became University of Toronto, Mississauga, and the first director of the Ontario Science Centre. We know that the understanding of Earth magnetism, whether it's the magnetic isochron on the ocean floor or paleomagnetism of continental rocks, provided some of the key evidence for plate tectonic theory. So today we're very excited to have invited Professor Catherine Johnson to tell us a bit about the magnetic fields of terrestrial planets. Professor Catherine Johnson is a professor of geophysics at the University of British Columbia and a senior scientist at the Planetary Science Institute at Tucson. Her research focused on understanding the structure and interior evolution of terrestrial planets, moons, and asteroids. She was a principal scientist on the Messenger, Mercury mission, and is currently a co-investigator on the InSight Mars mission and OSIRIS-REx mission for the asteroid Bennu. She's the fellow of the American Geophysics Union, and in 2019 was the recipient of both the IAGA Simcoe Award and the prize medal for the Royal Astronomical Society, which was awarded for investigation of outstanding merit into the formation and composition of Earth and planets. So without further ado, I'll let Professor Johnson take over to talk about the ins and outs of terrestrial planets, a magnetic field perspective. The stage is yours, Professor Johnson.
Thank you very much. Thank you for that really lovely introduction. And I would like to say I'm delighted and really honored to be invited to give this seminar today. So I'm going to talk, as the title says, about the terrestrial planets, specifically those in the inner solar system from a magnetic field perspective. And in the spirit of J. Tuzo Wilson's work, I'm going to stay very close to the observations. So I'm going to talk about what some of the observations tell us. I'm going to focus the story today on Mercury and on Mars, tell you some of the things that the observations tell us about the way that those planets work today and have worked in the past. The observations raise lots of puzzles and dilemmas. I'm not going to have time to talk about the resolution of those or some of the interesting aspects of them in this talk, but I really hope we can get into them in the discussion section. Many of them I have thought about myself, and some of them not so much. So hopefully we can have some good discussions. And before I start, I would like to say, this work, of course, hinges on the work of many, many people, and many people in my group over the years. But in particular here, I'd like to give special thanks to Anna Mittelholtz, who contributed and led much of the work that we have done together recently on Mars's magnetic field, and Lydia Philpott and Manar Al-Assad, who both worked with me on Mercury's magnetic field. And then also in particular, Roger Phillips, who passed away just over a year ago. He was never a formal advisor to me, but was very much an advisor and a co-conspirator along the way, and I miss his discussions and his guidance very much. Okay, so why care about planetary magnetic fields? They really tell us about a planet from its deepest interior to its interaction with its external environment. If a planet has today or has had in the past a global magnetic field, this tells us something about it provides constraints for the way in which the planet has cooled over time and its interior composition, particularly the composition of its metallic core. If it possesses crustal magnetism, so magnetized rocks in the crust, this tells us and gives us constraints on crustal mineralogy and the history of events that have happened to that crust. And then whether or not a planet has either of these two types of magnetic fields, or in fact an atmosphere, very much determines how it interacts with the solar wind. And that in turn gives rise to what we call external magnetic fields, typically time varying. And these circle right back into thinking about the interior, because those time varying fields can induce secondary fields, secondary currents in the planet's interior that result in magnetic fields. And those induced currents are very sensitive to electrical conductivity, which in turn is related to the thermal environment, volatile content, and the composition. So when we come to look at the planets in our inner solar system, of course, they're very different from each other on their surfaces. I'm going to include the moon in this discussion here. They're broadly similar in their interior structure in that they are all what we call silicate planets. They all have a metal core and a silicate mantle and crust surrounding them. But the proportion, the metal silicate proportion for each of those planets is quite different. For the Earth, Venus, and Mars, the metal core makes up by radius just under 50% of the planet. The Moon and Mercury are quite different. Their cores, in the case of Mercury, is less than 20% the radius of the planet, so very small volumetrically. And Mercury is almost the opposite. It's essentially just a big iron ball with a little bit of rock on its outside, sitting there closest to the sun. So if we just take a first look at the magnetic fields of those planets, do they have a magnetic field today, a global magnetic field? The answer is yes for two of them. I'm going to talk a lot about Mercury here. And of course, we know that the Earth has a dipolar field, very important historically for navigation, of course. None of the other bodies have a present day field. Do they have crustal magnetization? The answer is yes for all of these bodies, with the exception of Venus, where there isn't evidence currently for crustal magnetization, but we haven't had observations quite low enough to perhaps detect some if it's there. So that's an open question. Do they have an atmosphere, which can, of course, become charged in its uppermost parts and lead to electric currents that generate magnetic fields? And of those bodies, two are airless, Mercury and the Moon, and the others have atmospheres, albeit very different ones from each other. So even if you look at these 5 bodies in the inner solar system, just from these 3 perspectives, not one of them is exactly alike to another. And so we can expect that their interactions with the solar wind are very different, but importantly here from the perspective of a planet or a moon's evolution, clearly these have undergone very different evolutionary paths, and clearly partly the magnetic fields are a story or a piece of that story. Okay, so as I said, I'm going to focus on some recent work from Mercury and Mars, and I'm focusing on those because I think that they really have led to a revolution in our understanding of the magnetic fields of those bodies, and because for both of those bodies, there are upcoming and future missions that can give us even more information. The Moon has also been studied a lot over the last decade, but I'm not going to focus on that here. Of course, among these bodies, one of the things that is really different for all of them are the types of data that we have. And probably the most critical of this is actually having rock samples. Of course, for the Earth, we know a lot about the Earth's magnetic field because we have rock samples that we can study in the lab, that we can date in the lab, and we know where they're from, and we know mostly what has happened to them. In the case of the moon, we do have some samples from the Apollo mission. We also have meteorites. In the case of Mars and Mercury, we start to get very thin in terms of our rock record, our true rock record. We have meteorites from Mars that we can look at as analogs, although we don't know exactly where they came from on the surface of Mars. For Mercury, we don't even yet have a known meteorite from Mercury. So this is just something to bear in mind in terms of thinking about the magnetic field histories and what we can infer for these planets. Okay, so when we think about planetary magnetic fields, particularly global planetary magnetic fields, we need to think about what's needed to actually generate one. And there are some essential ingredients. Of course, you need a metallic core. It needs to be at least partly fluid. The planet needs to be rotating to organize the flows and organize the magnetic fields that are generated. But the key part that links the history of a magnetic field to the planet's evolution overall is that you need power to drive a dynamo field in the core. And for the simplest types of dynamos that we might think of, that power is driven purely thermally. So what you need is sufficient heat flow out of the core. So in this figure indicated by Q, core mantle boundary, sufficient heat flow out of the core that it exceeds at the bare minimum the adiabatic heat flux in the core. In essence, it actually needs to be bigger than that by another amount. It needs to exceed both the combination of the adiabatic heat flux and also any dissipation involved in generating the magnetic field, viscous or what we call ohmic. This is, for most planets and moons, very difficult to achieve, just thermally driven dynamos throughout a planet's history. And so for most cases, one needs to also consider some other source of power, and that can come from essentially solidification of an inner core. You get some power from the latent heat of solidification, and then also some additional buoyancy-driven convection that results either from release of light elements as the inner core solidifies, or the dripping down within the core of iron metal from somewhere near the core mantle boundary. So these are the key ingredients that are needed to actually explain planetary magnetic field history. When we think about crustal magnetization, so an important concept for that is to think about how rocks can acquire or lose magnetization. There are essentially three ways. They can gain a magnetization thermally as they cool in a magnetic field. They can actually gain one through shock processes or through the generation of alteration products, what we call a chemical remnant. So if any of these things happen in the presence of a magnetic field, you can get a net magnetization in the rock. If they happen in the absence of a field, the rock will remain magnetized, or if it was previously magnetized, become demagnetized. So these processes are very important in planetary magnetic field studies. Most of the inferences are based on the assumption that a magnetization was acquired thermally. We don't always know this to be the case, but one of the reasons to think about that first, at least, is of these three processes, it's the one for which we have the best physical understanding, but I'll come back to this later in the talk. Okay, in terms of thinking about interaction with the solar wind, there's sort of two main categories of interactions that we're going to think about here. One is where a planet such as the Earth or Mercury, which has a dipole field, interacts with the solar wind, and that dipolar field is draped into this windsock shape here. So here the solar wind would be coming from the right, and the planet's magnetic field is distorted, but most importantly is confined within this region called a magnetosphere. And what's actually happening here is there are electric currents that are being set up on the boundary of this region, and in fact in its tail here, that results in this confinement of the magnetic field. And these magnetospheric fields can be time varying. At the very least, you can see in this picture, the side on the right, which is the day side of the planet, looks very different from the night side of the planet. In the case of Mars, Mars doesn't have a global field. It has what we call an induced magnetosphere, but importantly, it does have an atmosphere, and that can become charged on the day side and in the ionospheric region, and not charged on the night side. This results in currents, forming electric currents. And so these can generate magnetic fields. And so these time-varying fields from external sources can either be our noise or our signal in planetary magnetic field studies. And I'll talk about both aspects here. Okay, so I'm going to spend the first part of the rest of the talk on Mercury and then a little bit on Mars. So turning first to Mercury, most of our knowledge about Mercury until about a decade ago came from Earth-based telescope and radar observations, and from flybys of Mercury by the Mariner 10 mission in the 1970s. So from the Earth, we knew Mercury's size, we knew its distance from the sun, we knew its rotation rate, its orbital period. We actually knew from Earth-based radar observations that there were bright materials in craters near the poles of Mercury. And from the flybys from Mariner 10, we were able to image half of the planet, just half. And we also learned that from the gravity signals acquired from Mariner 10, that Mercury's metallic core must be very large relative to the size of the planet. So this was the first indication it was really quite different from other terrestrial planets. Mariner 10 also measured a magnetic field, but we didn't know the source of that magnetic field. Was it generated in the core? Was it crustal? Was it actually just induced by the solar wind inside the planet? So the Messenger mission, which launched in 2004, flew by Mercury 3 times and then went into orbit for 4 years, was really designed to address a number of key questions about the history and evolution of, or history and formation of Mercury. One of these questions was, what is the nature of Mercury's magnetic field? Is it a core field? Is it a crustal field? How does Mercury interact with the solar wind? The Messenger carried a magnetometer here, seen here, out on a long boom to be away from spacecraft magnetic fields. And we're going to look at the results from that data set here. The Messenger was in a very eccentric orbit around Mercury. A couple of orbit examples here are shown in blue. And this has really important consequences for geophysics. The geophysical knowledge of Mercury from Messenger really pertains to the northern hemisphere, because that's where the spacecraft was close enough to the planet to give good gravity measurements, good magnetic field measurements, to be able to use the laser altimeter to get at topography. So from these observations, we learned just from even the 3 flybys in 2008, 2009, that Mercury has a global scale planetary magnetic field, and that its magnetosphere is very small, so that planetary magnetic field is weak, the magnetosphere is small, and the magnetospheric size is often denoted by this, what's called the subsolar distance. And at Mercury, this subsolar point of the magnetopause above the surface of the planet is just under half a Mercury radius. At Earth, it's about 11 Earth radii away. So it's a vastly different body in terms of its magnetic field strength and its magnetosphere. This is really important for magnetic field observation, because it means that in this very eccentric orbit, Messenger only spent a small fraction of time in that orbit inside the magnetosphere. And in terms of figuring out what part of the magnetic field that was measured comes from the planet versus from these external sources, this is very difficult because you never get very far away from the magnetopause. And those fields, due to currents on the magnetopause, co-vary spatially with the internal field. So typical approaches that we would use in geophysics, where you would take this as a potential field problem, you separate the internal and the external parts based on how they grow or decay with your distance from their source. Those don't work here. And in particular, they don't work because this is not a current-free region. You're actually flying across the current sources. So one of the big challenges here that I think Tuzo Wilson would have appreciated was that you had to think about the data set in a very different way. One of the advantages of this data set is that every orbit goes inside and outside the magnetosphere. So on every orbit, you can look and see where do I cross the shock? Where do I cross the magnetopause? And is there anything else that I can think about in terms of the data set? So you can map out the structure of the magnetosphere even before you start really to think about the details of the magnetic field close to the planet. So here's an example from one orbit. Time is on the x-axis. You can just look at the black line here, which is the magnetic field strength and its mirror here. And the others are the components of the magnetic field. So at 1, the spacecraft crosses the shock, and you can see this from this increase in the field strength. And inside that, the field is very variable in this sheath region. And at 2, you move into a region where the field is very smoothly varying and much less noisy. That's inside the magnetosphere. And then you pass out over the shock again. And typically these boundaries, you can pass over them multiple times in one orbit because they're moving back and forth over the spacecraft with the speed of the solar wind at 400 or so kilometers a second. You can also see on each orbit where you transition from a field that's pointing towards, if you're on the night side, towards the sun in the northern hemisphere to away from the sun. And so that region there is the magnetic equator, and it's just shown here on this figure. So you can look at this on every orbit. So this is a big data exercise, but you can use basically all of your observations to map out these boundaries. Here's one example. This is these are the magnetopause crossings from MESSENGER. They have this funky donut shape because of the orbit. So we're always crossing them kind of in this funky region here. I'm going to talk about the colors in a minute. But what you can do then is take those, assume that the magnetic field is more or less the magnetosphere is symmetric about the equator, the magnetic equator. And so you can map them all onto this northern boundary here. And so you see that these really define a very nice shape of the magnetopause boundary, shown here by a couple of different models. The inside one is the more correct one here. The white dashed line is a model for the magnetopause boundary. The color coding on this, I'm going to come back to. The color coding actually denotes the distance of Mercury from the sun at the time each magnetopause measurement was made. And dark blue means closer to the sun, and yellow means further away. So it's clear that something's going on here. The magnetopause is moving toward or away from the planet, but you have this average structure to it. This is the planet's geographical equator. And here are the observations of the magnetic equator. So what you see from these is that they are offset with respect to the magnetic equator, and they're not really tilted. And so just from these observations, before one even tries to take magnetic field data inside the magnetosphere and actually understand more about the geometry of the field, you can see that this magnetic field is dipolar, it's offset. It's very symmetric about the planet's rotation axis, and we can really see that when we look at the radial component of the field here. This is all the data now plotted inside Mercury's magnetosphere. The North Pole's at the center, the dashed line is the geographic equator. You see that the field increases in its strength as you go from the equator to the pole, and that it's a negative radial field. So the field lines are pointing down towards the North geographic pole here. And you see from this plot that it looks actually very boring, right? It looks very symmetric about the planet's rotation axis. So you can use these observations together then to actually build a model in which an empirical model in which you prescribe currents on the boundary that's given by your magnetopause crossings, currents that are in the tail region whose location is given by the magnetic equator of the planet. And then you can build this empirical model in which the internal field is a dipole field. And all you need to do is vary the strength of that dipole field, calculate the field due to currents on this boundary here that would be needed to shield the entire thing inside this magnetosphere. And that enables you to get an estimate of the dipole strength of the field. So from this, we know that Mercury's field is very weak, it's dipolar, its magnetic equator is offset north of the geographic equator, and it's very axisymmetric. all of those aspects actually make Mercury unique in the entire solar system in terms of its magnetic field. So then the question from a geophysics perspective is, well, that's kind of cool that it's so different, but it's also sort of boring. Is it just really this very axisymmetric thing and that's all there is to it? We know that the Earth field has quite a bit of non-dipolar structure in it. And the reason to ask if there more for a planet is that, for example, at the Earth, we know that this non-dipolar structure is actually quite diagnostic of some things about the deep interior, in particular about the boundaries of the inner and outer core and the outer core and the mantle. So the regions that are important in the generation of magnetic field. So it's diagnostic of core mantle boundary heat flow pattern, possibly lower mantle electrical conductivity of the inner core size. And it's even more obvious when we look at this plotted at the Earth's core mantle boundary. The non-dipolar structure then really starts to stand out. So this is actually very difficult to get at for Mercury. And I know that Alain Plattner talked to you a couple of weeks ago about our work trying to do this at Mercury. It's difficult because although this magnetospheric model that I have described to you does a very good job of matching the data overall, so it actually matches about 90% of the signal in the data, most of the leftover 10% has nothing to do with internal magnetic field sources. It's about dynamics in the magnetospheric fields and the interaction with the solar wind. And you have to get rid of that to look at what's left over. And Alain talked about this in a lot of detail. So this is the lightning talk slide version of his talk, just to remind you that there are ways to do that. And he talked about this at length a couple of weeks ago. And when you do that, what you find for Mercury is, number one, you can only look at the leftover signal over the northern hemisphere, because this is where the spacecraft altitudes were sufficiently low. But when you do that, what you see is a magnetic field pattern that is large in spatial scale. That's what we can resolve at this point. And it's given by the left-hand figure here. And then in the two other figures, the color in the middle figure is the gravity field, and in the right-hand figure is topography. And in the middle figure, the contours of the magnetic field that's in the left figure. So what you can see here is that the magnetic field structure that's left over actually correlates very well with this feature called the northern rise. And so one of the things that Alain and I looked at is, where is this regional scale magnetic field coming from? Could its source be in the crust or the lithosphere, which might be expected because of this correlation with gravity and topography? Or is it deeper? And what we found was that this is actually a core field. So this is part of Mercury's non-dipolar field. It's very small. It's on the level of sort of 5% of the dipolar field, but it's coming from the core. And the question is why, what's happening in this region? There are various ideas that the northern rise may be supported by buoyant deep support in the mantle. So maybe this is an area that's a prime candidate for coupling of lower mantle and core processes. Okay, so I want to come back to this figure that I referred to earlier that shows that Mercury's magnetopause actually changes in its position depending on where Mercury is relative to the sun. So what's happening here is that Mercury's heliocentric distance varies by about 50% during a Mercury year. When it's closer to the sun, the solar wind dynamic pressure is higher because the solar wind density is higher. And so when Mercury is closer to the sun, the solar wind dynamic pressure compresses the magnetosphere more than when Mercury is further away from the sun. And this is actually very important because if we were to look at the surface of the core and look at the magnetic fields that are generated by the currents on the magnetopause, as seen by the top of the core, it would look something like, on average, this picture in the middle here. So on the night side, not much because you're far from the magnetopoles. On the day side, fields of a few tens of nanoteslas compared with about 300, 400 nanoteslas from the dipole field in the core. So this is sort of on the level of 10% of the dipole field. And when Mercury's magnetosphere is more compressed, right, this can increase substantially to well over 100 nanoteslas on the day side, and much less when Mercury's magnetosphere is less compressed. So this compression and expansion happens on an annual timescale. It also happens on much shorter timescales, but we have 16 Mercury years. So we actually have of observations. So we have a good estimate of this periodic contraction and expansion. And this is important because it's a time-varying field. It's time-varying on the timescale of a Mercury year, which is 88 Earth days. And this time-varying field will induce currents, electric currents at the top of the core that will be generated in a way to try to resist this change. So if the solar wind is trying to compress the magnetosphere, the currents that are induced will try to resist that a little bit. And this is actually important for two reasons. One's a geophysical reason in terms of understanding interior structure, which is that the strength of these secondary induced fields are very sensitive to the ratio of the core to the planetary radius. So it's a way to actually map the radius of the core. And the second is that it reduces the compression of the magnetosphere on the day side. And a big question before MESSENGER was how much of the time does the magnetopause reach the planetary surface? So you can look at this in a couple of ways, and we did that. You can basically look at whether or not the magnetosphere compresses and expands as much as you think it should. And the answer, if there were no induction, and the answer to that is there is induction. And then you can say, is that restriction on the compression and expansion the same that you would expect based on any changes in the dipole moment that you infer, for example, at its closest distance from the sun from its furthest distance? So you can estimate these induced fields in two independent ways. And both of them actually provide really nice constraints on Mercury's core size. Basically, that it is very similar to the core size of 2,000 kilometers, that was 2,000 to 2,020 kilometers, that was inferred from geodetic techniques. And it allows you to think about how much of the time the day side of the planet is exposed to the solar wind. Okay, so I want to talk about Mercury's crustal field, just to round out the story about Mercury. For most of the MESSENGER mission, the spacecraft was too far from the planet to detect any crustal fields. But right at the very end of the mission, so this green and red curve is the distance of closest approach of the spacecraft to the planet. Right at the end of the mission, about 4 months of the time, for about 4 months, it spent most of its orbit below 80 kilometers. And of course, at the very end of the mission, it was at 0 kilometers. And this figure on the right-hand side just shows a map of that. So you see these altitudes that are less than around 30 kilometers in the sort of blue-green color, and up to, in this figure, 60 kilometers in the pink color. And at those very low altitudes, we detected really small signals that are clearly of crustal origin. We know they're of crustal origin because of the way they decay with altitude. And so from those small signals, we can build a map by inverting them, make a map of essentially the magnetization strength over the surface. And so this is such a map here. What you're seeing is the magnetization strength. Assuming that the magnetization is in the upper crust, we can't actually say exactly where it is. We don't have depth sensitivity. But assuming that it's carried over a layer that's on the order of 10 kilometers, if you make the layer thinner, you increase the magnetization and vice versa. And so there are some important observations here. First, you see that this very spatially, it has some association with geographical provinces, notably this region up here in the top right quadrant, which it comprises the caloric basin. So that's the brown region above and behind my head on my background, and the top right hand of the figure here. And those are the regions of strongest anomalies. There are some strong magnetic fields over some, but not all craters. Unlike the case on Mars, there's no correlation with crater age, basin age. But there are sort of ubiquitous weak magnetizations. And the first question to ask for Mercury is this crustal magnetization just induced in the present day field? In the case of the Earth, the crustal magnetic fields that we see come about 50-50 from fields induced by the present global field and remnant crustal fields that are indicative of magnetization acquired at some time in the past. For planets other than Earth, it's actually difficult to sort this out, planets with a global field like Mercury. But the best insight that you can get, I think, comes from asking the question, is the magnetization that you infer consistent in its strength with what you would expect if it was acquired in the present day field? Because we know what the present day field is. And so then the other thing you need to know is the magnetic susceptibility of the rocks. Essentially, how efficient are they at recording a magnetization in a given field? So this is where not having rock samples is very important. We don't know what the susceptibility or the range of susceptibilities is for Mercury. A very important aspect for Mercury is that geochemically, the conditions under which Mercury's mantle and crust form were very, very reducing. And so it's likely that the magnetic carriers that are present, they're most likely to be essentially native iron nickel carriers. It's so reducing even that magnetic sulfides are barely possible under Mercury conditions. When you go through this exercise and use susceptibilities that would be appropriate for the amounts of iron that we think are present in Mercury's crust, the answer that you get is that most of the region on this plot on the left-hand side that's sort of greenish in color could be magnetizations that are induced in the present field. But in the other region, the magnetizations are too strong to be induced in the present day field unless the rock properties are very different from what we think. So the inference here is that at least some of this magnetization is remnant and was acquired in an ancient field. So there are some puzzles and some inferences. We've really kind of completely, I think, changed our understanding of Mercury's magnetic environment here. The puzzles are what makes this present day field like pattern and weak strength, what gives rise to this northern rise anomaly. Can we do more with time-varying fields than estimate the core size? What are these issues about crustal magnetic mineralogy? And really, what are the constraints on the timing of the ancient field? And these all need to be put together with other aspects of Mercury's history. And hopefully we can have some discussion of this in the discussion time. In terms of future observations, the Bepi-Colombo mission to Mercury is en route. It already has had one flyby of Mercury. From a magnetics perspective, it will be an amazing mission. It carries two spacecraft, one that will be more in the solar wind and one that will be closer to the planet. And these joint measurements will be very important for understanding solar wind interactions. Okay, I want to talk a little bit here with what time we have left about Mars, because this is another planet for which our view of its magnetic environment is really changing and is sort of prime, I think, for new developments and sort of really new revelations. So in terms of magnetic field data sets from Mars, there are two sets of satellite observations, one from Mars Global Surveyor, which orbited the planet about 20 years ago, and one from the MAVEN spacecraft currently orbiting the planet, and one set of surface observations from a magnetometer on the InSight mission. So if we want to think about Mars, Mars has no global magnetic field today. And here's just a little primer about what's where on Mars, in case you don't think about Mars every day. The northern and southern hemispheres of Mars are very different. It's what's called the north-south dichotomy. The north is lower, less heavily cratered compared with the south. There's a major volcanic province, the Tharsis province, that includes these very large volcanoes, Olympus Mons and the Tharsis Mons. There's also a second large volcanic province, Elysium. There are major impacts, at least impact basins, at least 4 of which are agreed on. Many are not agreed on, but these 4 are agreed on. And they probably happened around 4 billion years ago. And then there's evidence for surface water, very different climatic conditions in the past from these valley networks that occur mostly close to the dichotomy boundary and in the southern hemisphere. And in terms of what happened when, you can see this timeline along the bottom in billions of years, volcanism throughout the planet's history, but most of the volume of Tharsis formed very early in the planet's history, prior to most of the valley networks here, and then the impact basins not shown around 4 billion years. So no global field today, but the Mars Global Surveyor mission flew close enough to the planet to detect fields that were regional and local in scale that are inferred to result from crustal magnetization. Many global magnetic field models have been built from these observations. I'm showing just one on the right-hand side. It's the radial component of the magnetic field at about 200 kilometers above the surface of the planet. And you see some associations with these major physiographic provinces. You see some evidence for the north-south dichotomy in the magnetic field. Most of the strong fields are in the southern hemisphere. An important point here is these magnetic fields are about 10 times stronger than the magnetic fields resulting from terrestrial crustal magnetization. So these are very strong magnetic crustal magnetic fields. There is very little magnetic field over most of the Tharsis region, over most of the impact basins, and that many, but not all, of the strong anomalies are at least spatially correlated. Whether they have anything to do with it or not is up for debate, but they're spatially correlated with where we see valley networks. So the inference from this for a long time from Mars Global Surveyor data has been that these are strong magnetizations, as I just mentioned, and this is indicative, obviously, of a past magnetic field, probably very ancient because most of the strong anomalies are in the southern hemisphere. And the key constraint to thinking about timing of the magnetic field has always really come from the one observation of the absence of magnetic fields over these big basins. And the thinking was either that those basins in the middle of this figure formed before the magnetic field started. So they and any other crust that formed before the magnetic field started are unmagnetized. And the anomalies that we see result from a field that happened after these large basins. This is tricky because those strong anomalies are over the very ancient southern hemisphere in which the basins sit. So most people actually favored the alternative scenario in which most of the southern hemisphere was magnetized, the dynamo had switched off by the time these basins formed, and the thermal and shock effects of the impacts demagnetized the regions in the interior of these basins. And there's a really big issue in thinking about Mars's crustal magnetic field in terms of temporal evolution. And the big issue really is whether or not you can assign the age of the surface unit to the age of the magnetization, right? So these arguments that say this region is very heavily cratered, it has an age of X, and it's magnetized, therefore the age of the magnetization is also X, requires that it's this near surface layer that's magnetized. If it's not the near surface layer that's magnetized, then all bets are off, right? This deeper layer could have been magnetized earlier, the top layer is younger, or it could have been magnetized later if it's in a volcanic region in which there were lots of intrusions. And the really key issue here is that it's very difficult to associate magnetic anomalies that you see at several hundred kilometers altitude with surface geological features, because your resolution, the rule of thumb is that the maximum resolution, so the minimum resolvable wavelength, is on the order of the spacecraft altitude. So for Mars Global Surveyor, on the order of 400 kilometers. Fortunately, now we have MAVEN, and the MAVEN spacecraft is actually spending some of its orbit much closer to the planet than Mars Global Surveyor. And so we have data from lower altitudes. And so one of the great things that we've been able to do with MAVEN data, and this has really been work by Anna Mittelholtz and myself, has been to look at the MAVEN data to see if there are regions where there's additional structure that can give us some clues about the timing of the dynamo. One area that we've looked at in detail that I'm not going to talk about here, except for its take-home point, is the Northern Hemisphere, specifically to ask the question, was the absence of magnetic fields over the Northern Hemisphere in Mars Global Surveyor data just a resolution issue? There are fields, but they're weaker. And the answer to that is actually yes. And the places where those fields occur are regions in the Northern Hemisphere that seem to have been unaffected by later impacts or reheating. And so we inferred that these weak magnetizations in the Northern Hemisphere probably were acquired at the time that crust was formed. So likely at the time that this dichotomy formed. The interesting area that I'm going to talk about here is this region with the smaller black circle around it in the map. This is actually a volcanic province, a small volcanic province. There's a volcano here in red on the geological map, and you just see the little blip on the topography. This is a volcano that was last active, we think, about 3.7 billion years ago, so after formation of the major basins. And this sort of white-gray puce-colored unit here in the geological map is a pyroclastic flow that's thought to have been sourced from this volcano. And the scale bar here, each of these grid cells in here is around 500 kilometers. So this is an enormous flow, right? This is almost 1,000 kilometers across. There were magnetic field data from Mars Global Surveyor over this region. There was a suggestion that it might be magnetized, but this was subject to this same, in terms of interpretation, the same problem. We don't know whether the surface unit is magnetized or whether the magnetic fields that we see over this region are in fact just from buried Southern Hemisphere units that were quite strongly magnetized. So you couldn't distinguish between these. So actually assigning the age of this unit to the magnetization was not possible. We now have MAVEN observations at lower altitudes over this region. And so this is an image of the region here. What I'm showing is the tracks in color are basically the MAVEN orbit tracks, but they're color-coded by the strength of the magnetic field along the track. And then the magnetic field is also given its wiggly white lines here. And what I want to draw your attention to is the low in the magnetic field that's actually associated with the region where the tracks pass over this crater. This is a crater that's about 35 kilometers across. Its extent in terms of modifying the terrain around it is 2 to 3 crater radii. And what we see in the magnetic field is a decrease in the magnetic field associated with this crater. And we inferred this we suggested that this might result essentially from a demagnetization or essentially a hole in a magnetized unit. And you can do some forward modeling to actually predict what you would see if that's the case. So you make the hypothesis that this pyroclastic flow, which is 1 to 2 kilometers in thickness, was penetrated almost to its base by this crater, which is completely plausible from the geology of the region. And you actually explain most of what you see in the magnetic field data from this. And this is really exciting because this is actually the first evidence, I think, for anywhere on Mars where you can definitively say that the surface unit is actually the one that's magnetized, and we know the age of the surface unit. And so from this, we can infer that the age of the magnetization in this region really was most likely the age of the unit itself, 3.7 billion years. Some other cool things, because we know the thickness of the flow, the thickness of the unit, we actually know not just the vertically integrated magnetization, but the magnetization strengths. So we can compare that with terrestrial flows and actually get better bounds on the field strength in which the magnetization was acquired, which is actually turns out to be Earth-like. So this is actually some really, I think, new results in terms of thinking about Mars, evidence from the northern hemisphere, a dynamo at the very earliest times in Mars's history, and evidence from somewhere else of a dynamo much later in Mars's history, specifically at the times at which also there is evidence for surface water. So this is actually really interesting in terms of thinking about the history of Mars, a puzzle here. We don't know what happened in between, and we can talk about that in the discussion section. So now we can turn to just some observations from the InSight mission. InSight mission is, of course, a geophysics mission. Primarily, it has landed a seismometer on the surface of Mars. The primary purpose of this mission is to determine seismicity and interior structure. But as one of the additional environmental sensors, it carries with it a magnetometer. The magnetometer is to measure magnetic fields, specifically for the purpose of actually making sure that we can decorrelate those signals from the seismometer. So the key thing for our purpose is that the magnetometer was not put on the mission with specific science goals in mind. So it's not ideal for science investigation. Specifically, it's not in an ideal place in terms of magnetic cleanliness. It sits right under the deck between the two solar panels. There was very limited calibration done. So we've done a lot of work to rule out sources or to try to minimize in our process data effects from the lander and time varying and static fields. But what you can do is look at the magnetic field that is measured by InSight on the surface. So what's shown here is the magnetic field strength as a function of local time during a day. So 12 is noon here. And that is a function of Sol, so day number on the surface of Mars. So this is one Mars year here on the axis. And the thing that I want you to focus on just now is just the magnitude of the scale, the color scale. The average amplitude of that field, it varies during the day, and we'll mention that in a moment, varies during a day, but the average amplitude is about 2,000 nanoteslas. And we can compare that with what we predicted from satellite-derived models. And what we predicted at the landing site was more on the order of 200 to 300 nanoteslas. And so why this difference? The difference is about the fact that the satellite data themselves are not sensitive to shorter wavelengths magnetization. So at the surface, you're seeing the effects of much more local magnetizations. And I'm going to skip, in the interest of time, the next couple of slides, except to say that we can combine this observation with knowledge of the geology below the InSight landing site to ask the question whether these results could you have magnetizations carried in units that are of similar or younger age to the age of the Lucus Planum unit? And the answer to that is yes. So I'm just going to skip over that slide. Okay, the last thing that I want to mention, and I'm just going to show this one slide with respect to this, is that an exciting piece of having a seismometer or having a magnetometer on the surface of Mars, it's really exciting to have a seismometer there, but from the magnetic field perspective, an exciting thing is to be able to look at time varying fields, because these are the fields that you would like to know about. First of all, to better understand the ionosphere, and secondly, to understand the interaction of the solar wind with the planet. Thirdly, to be able to use as sources to potentially do magnetic sounding of electrical conductivity. And the place where I'll leave this story is that we have measured time variations in the magnetic field that have seasonal periods, that have diurnal periods, that are waves with much shorter periods. So these three different sources are from the ionosphere, possibly from the magnetosphere, the induced magnetosphere. We've also measured magnetic fields that suggest that there are diagnostics or signals of space weather at the surface. And we're looking at whether or not there are magnetic signals associated with dust movement, so dust devils on the surface. So these are, I think, really exciting avenues for future investigations, in particular for the time-varying fields perspective. Are they similar elsewhere on the surface of Mars to at the InSight location? It would be really nice to have a primarily magnetic field sort of science investigation in other places on the surface. And then this issue about the dynamo timing, exactly what happened, what kind of a dynamo was present to actually produce dynamo fields at 4.5 billion years and at 3.7 billion years. Does the field being present at 3.7 billion years allow the possibility of actually a substantial amount of chemical remnant magnetization on Mars acquired through hydrothermal alteration in this warmer, wetter climate? And then, you know, the big elephant in the room, I think, for magnetic field studies is, what's the story of the big basins? Are they really unmagnetized, completely unmagnetized, which would mean one of at least three things. One, there was no dynamo present at the time they happened. And or two, they excavated all of the magnetic material in their interiors and there was nothing left to be remagnetized. Or three, that the dynamo was basically intermittent or reversing at the time these formed. So a lot more to do in terms of crustal magnetic fields, understanding them. One of the big things, as I mentioned, is we don't have samples from Mars, but eventually we will. The Mars 2020 mission actually landed on units that have the same, some of the units have the same age as the Lucus Planum unit. And so stashing a sample from this unit would be really important for magnetic field studies in the future. The Chinese Tianwen-1 mission has a magnetometer on it that operates for about 40 minutes a day when the rover is roving. ExoMars will carry a magnetometer. So lots of potential for future measurements. One of the things that as a geophysics community we've been plugging for is actually lower altitude measurements by balloon, by potentially by helicopter now at Mars, or lower altitude measurements over kind of regions to get at the regional scale, high resolution crustal magnetic field, particularly over some of these regions where we know there was water in the past. So I'm going to leave it there. We can have lots of discussion of these or any other issues that people would like to discuss. I'm just going to leave you with some pictures here. Thank you very much.
Thank you very much for this really fascinating talk.